Okay, so today we are going to discuss what is uh, a real number. For example, in our class 8 or 9, we come across with a number called root 2. Then we prove that root 2 is not an irrational number. Then what is it? What is an irrational number? So, that is what we would like to discuss, because most of us we say that okay, a number which is not rational is irrational. Then one can ask that what is a number? So, then number consists of rational and irrationals. So, it is a roundabout way of saying that where is your house now in front of my house and where is his house now in front of my house. We need to define something. So, today in this lecture we will try to see that what is a real number. We will not give the explicit construction of the real number, which is little hard, and let us see what we can do. So, as at a very early stage we get ourselves exposed to natural numbers 1, 2, 3, 4 like this. So, we also have algebraic operations like addition and multiplication. If we add two natural numbers, then the result is going to be a natural number. If we multiply two natural numbers, then we also get natural numbers. However, if you subtract, then we are not going to get natural numbers. So, now if we enlarge our set to set of integers, which means we add -2, -1, -3, 0, then we can in this set Z we can perform addition, multiplication as well as subtraction. But to divide, for division we need a set of rational numbers, which means any which is represented in the form of p by q, where q is not equal to 0. So, then in this set of rationals we can add two rationals, we will get a rational number, we can multiply, still we will get a rational number, we can subtract, we will get, and if b is not equal to 0, then we can divide a by b, and which is going to be a rational number again. So, then we come across with from the Euclidean geometry some number called root 2, which is the hypotenuse of a right angle triangle with each side is equal to 1 unit. And we know that this is a number, whatever it is we are going to get it from a Pythagoras theorem, and now this root 2 is not rational. So, therefore, definitely a need arises for more numbers, more than rational. So, one would like to say that okay, so let us take the rational numbers with that we have with us, and then consider all these number with the form a to the power b, where a is a non-negative rational number and b is any rational number. Then 2 root 2, square root of 2 is 2 to the power 1/2, which is of this form. Now, we have rational numbers, then we add all the numbers which are rational to the power rational. Will it be enough? So, then what we have seen is that if I take any circle, then what we know that irrespective of the size of the circle, if one divides the circumference with the diameter, then that is going to be constant, and that is a number which we call it as, we call this number to be pi. So, one can show that pi does not belong to the form of a to the power b. So, now then what So, what is the number we are looking for? Now, in a sense we agree that we are looking for a larger set which contains q, and this larger set x, for our purpose we must able to do addition, subtraction, multiplication and division. That means, what we would like to have a structure on this larger set x which contains the set of rationals q. If a and b, if I take from x, then a plus b will also be in x, and if a, b, c in x, then the addition prescription is there, and it is whether I add a plus b plus c first and then a, this will be same as I add a plus b and then c. So, order of addition is redundant, I can do it. Then there exists one element, let us call denote it by 0, such that I take any element of x and I have a prescription of addition. Now, if I add a to 0, this is going to give us a. This is true for all a in x, and also for every a we get some number b, let us call it for the time being as minus of a, such that a, if I add with that number, this is a symbol which is just I am denoting it by minus of a, that is an element of x, then this will give me 0. We have a prescription of addition in x in which we can do this operation 1 to 4. Then also we would like to have some prescription of multiplication. That means, if a and b in x, we have some notion of multiplication in x such that a into b, a multiplied by b, we still it will be an element of x. And then this associativity a into b c is equal to a b, first I multiply a into b, then I multiply by c. And there exists one element in x such that if it is multiplied, if I multiply that element with any other element of x, then I am going to get that element, that is a into 1. In this case I am denoting it by 1, a into 1 is equal to a for all a belongs to x. Now, for every a there will exist some number. If I multiply a in that number, it must give me 1, that I denoted by a inverse, and such that a into a inverse is equal to 1. This is true, and this a, there is a word of caution. So, this what I would like to say, that this a not equal to this 0 element, and now we have got two operation, one is addition and one is multiplication. So, now addition and multiplication should respect each other. A into b plus c is equal to a into b plus a into c, that is the distributive, and a plus b into c is equal to a into c plus b into c. Now, in fact, any set which has operation like plus and dot multiplication and satisfies all the above properties, we call it, give it a name, we call it as a field. So, as we can see that in Q all these properties are satisfied. So, in some fancy word we can say that Q is a field. Okay. So, now what we want our X, the larger set, to be a field which is going to contain Q, and then when we want to extend this Q, we are looking for a larger set. Now, let us look closely the set of rationals, what are other properties of the rationals are there. So, in that direction we can see that if I have two rationals, if you give me two rationals A and B, then either A is lesser equal to B or B is lesser equal to A. Either A is strictly less than B or B is strictly less than A or A is equal to A. That means, if you give me two different rational number, then one is bigger than the other. So, there is an order structure is inherent in the set of rational numbers. So, definitely what we would like to have for a larger set X, what we are looking for, which is going to be a field, not only which is a field, which any two element of that we must compare any two element. So, that is what it is called ordered field. So, now the point is that from Q we want a larger set X, and that what we want it to be an ordered field. Okay, so, now what kind of ordered field we are looking for? So, let's try to now look at what exactly we are lacking in Q. Now, for this I define a set, a subset of rational to be bounded above if there exists a x naught in Q such that x is lesser equal to x naught for all x in A. Now, for example, if I take all the rationals which are less than 1, then this is going to be a set which is bounded above, and definitely this any number of this set is going to be lesser equal to 1. Similarly, we can say that A is bounded below if there exists a x naught belongs to Q such that all those elements of A, they are greater or equal to this x naught. So, for example, if you take all the positive rationals, then definitely this set is going to be bounded below. Now, when so then in this case I will say that x naught is an upper bound, and in this case what I will say that x naught is a lower bound. Okay. So, now suppose look at the set of rationals which are less than 1, then definitely 2 is an upper bound, 1 is an upper bound, 3 is an upper bound, anything bigger than 1 is going to be an upper bound. Similarly, positive rationals, then 0 is a lower bound, minus 1 is also a lower bound. So, it not necessarily to have one upper bound or one lower bound. However, among all the upper bound, if we are looking for the least of the upper bound, that is called the least upper bound. So, now the definition, A is contained in Q, be bounded above. Now, if there exists a x naught such that x naught is an upper bound of A, that means every element of A, if I take, that is lesser equal to x naught. Now, if y is any other upper bound of this set A, now suppose there is another number y such that x is lesser equal to y for all x in A, then y is also an upper bound. Then in that case x naught is lesser equal to y for any other upper bound y of A, then we say that x naught is the least upper bound, or in short we write it LUB of A. Now, let us look at some example. Now, if A is contained in set of integers which is bounded above, that means there will exist some integer n for which all these element of A, they are going to lie on the left of this, then obviously what you can see that this A is going to have a maximum element. However, if we consider, let us say, a set of all rational, let me take to be positive rational to start with, positive rational such that x square is less or equal to 2, then definitely this set is bounded above. For example, if I take x equal to 2, 2 is a rational, and if x square is less than 2, then obviously x has to be less than 2. So, 2 is an upper bound, and you can think of various other upper bound. Now, does it, the question is that does it have a least upper bound? You see here the least upper bound, what we are trying to look for, we are searching for that least upper bound in the set of rational itself. As you can guess correctly that in this case the least, whatever the least upper bound you are going to get, that may not be a rational number. So, what we conclude that certainly the set of rationals does not have a least upper bound property. Similarly, one can define the greatest lower bound. You take a lower bound, there will be many other numbers which are also the lower bound, because your set is lying on this side. So, there will be many other lower bounds. Now, among all those lower bound, whatever is the greatest, that we are going to call it as the greatest lower bound. So, this is what is the definition. X naught is a lower bound of A, and x naught is greater or equal to y for any other lower bound y of A. Then we say that x naught is the greatest lower bound. So, if we consider the set A such that x square is greater or equal to 2, set of all rationals, let us say positive rationals, and where x square is greater or equal to 2, then obviously this is bounded below, because 1 is definitely is a lower bound for this set x A, but it does not have a greatest lower bound in the set of rationals. So, what we have seen is that the Q does not have the greatest lower bound property or the least. So, let us see for example of the least upper bound. If you take A to be 1, 5, 17, 20. So, this is the set which is bounded above as well as bounded below. Now, the upper bound can be 30, upper bound can be 40, and but the least upper bound is going to be 20. Similarly, the greatest lower bound is going to be 1. Now, if you look at the set little non-trivial, if you look at A equal to set of all n by n plus 1, and n is a natural number, which is of course greater or equal to 1, I am not including 0 here. So, in this case, as you can see that this is a bounded above, because any number greater than or equal to 1 is an upper bound, and similarly any number less or equal to 1/2 is a lower bound. In this case, the least upper bound is 1 and the greatest lower bound is half. So, now you can see that although the 1 is the least upper bound, but here the least upper bound which is 1, which does not belongs to A. So, one thing is that least upper bound may exist for a set A, it is not necessarily true that this least upper bound is going to be an element of A, that is what the least upper bound. So, now another example, if you look at take the set of all positive rationals, then A is not bounded above, however, A is bounded below. So, it can happen that a set A is bounded above, but not bounded below, or bounded below, but not bounded above, or the set A, when A is both bounded below and bounded above, we said that the set A is bounded. Now, what we have seen that we will call in a field when there is a comparison, we can compare ordered field means we can compare two elements. So, we will say that if we have an ordered field, it is going to have this is this the other way, the symbol is the other way, x contains q is said to have least upper bound property. If I take a subset A of x which is bounded above, then it must have a least upper bound in x. Similarly, the ordered field x is going, we will say that it has a greatest lower bound property. If any subset A which is bounded below, then there will be an element in x which is going to be the greatest lower bound for A. What we have seen in the previous slide earlier, that q does not have a least upper bound property. Now, naturally this thing what we lack in the set of rationals, now we will try to have it in our larger set x. There we have seen that if we include this least upper bound property, then automatically root 2 is going to be a member of the larger class x. So, this is now the difficult part which we are not going to prove, but one can show that, and we are taking it as an axiom that there exists a smallest ordered field R, which we denote it by this R, which contains q, which has the least upper bound property. So, this is the what is a real number what we are saying. This is a kind of a set which is an ordered field which contains the rational, and it also has the least upper bound property. Not only that, among there may be more than one such thing which contains q, which is an ordered field, which has a least upper bound property. What we are looking for is the smallest of that large set, smallest of that ordered field, that we call it as R, and it exists, that is what is our assumption. So, any element of that ordered field, we call this as a real number. So, any element, so definitely root 2 is this belongs to this real number, and one can show that R is also going to have, once it has a least upper bound property, automatically this is going to have the greatest lower bound property. So, here in terms of the field, what we have said that okay, you know that because R is a field, that means if I give you two real numbers, then you can add. If I give you two real numbers, you can multiply. If one number is a non-zero, then you can divide, and so on and so forth. So, that is what it now we have all the flexibility to do all this algebraic operation, and much more than that, even we can take. So, let us say that what are the other properties. A very interesting property of this is called the Archimedean property. Now, it is an ordered field, that means it will contain a 0 element 0. So, x is positive real number. If x is greater than 0, we say that positive real number, and there is another y wherever it is. Then I can always get a natural number such that n times that x is greater than y. You see, if y is negative, then the n equal to 1 is going to do. Now, suppose let us take y is strictly bigger than x, that means you have x here and then you have y here. Now, if I pictorially try to convince yourself, if I go, then 2x is this, I have a prescription of addition, then I add another x, I will go 3x is here, then I add another x, 4x is here, then 5x is here, 6x, then maybe 7x I am going to cross. So, which means at some stage if you keep on adding, that at some stage you are going to. So, I will end this lecture by the proof. So, this is the proof is now suppose that does not exist any n, that means what? N x is going to be less or equal to y for all n. Then definitely if I take the set A to be n x, n belongs to n, then y is going to be an upper bound of this. By the construction of the real number, definitely this set A is going to have a least upper bound, because that is what is our axiom of a real number. Now, call that least upper bound to be alpha. Then least upper bound is definitely an upper bound. So, which is going to be greater or equal to any member of this set A. Therefore, n plus 1 x is less or equal to alpha for all n, because n plus 1 is again in n, therefore, is in capital A in the set. That is n x is less or equal to n x plus x is less or equal to alpha, therefore, n x is less or equal to alpha minus x. But x is a positive number, therefore, alpha minus of x, this is less than alpha. Now, alpha minus of x is less than alpha, and alpha is the, and here this says that this is true for all n, therefore, alpha minus x is an upper bound of A, but alpha is the least upper bound. How can we get an upper bound which is less than alpha? So, that contradicts the proof. Therefore, this our assumption that suppose n x is less or equal to y is wrong. Therefore, there will exist at least one n for which n x has to be bigger than y. Okay, thank you for your attention, and in the next lecture we are going to discuss some more properties of the real number and also what we can do, and we will try to play around with this real number in the next lecture.